Hello, my name is Leno. I'm a site reliability engineer at Clever Cloud. Today I'll be talking to you about Maestro, which is an operating system that I'm writing from scratch using the Rust language. So I am programming since I'm 10 years old. It's my favorite activity, actually. I created Maestro because I wanted to do that for a long time. And I've actually made a blog about it. So if you want to know more about the project, you can check it out. I highly recommend it. I cover topics that are pretty technical. I dive into the project itself and into the code. So yeah, check it out. Clever Cloud is a European company that provides cloud services. So our goal is to basically make the life of developers easier. So you just push your code to our infrastructure, and we handle all the rest, so the deployment, scaling, and the link to other components. We handle all of that for you. And we have a highly technical stack. So we have customer implementations of some components, so we can get the best performance for the hardware. So Maestro is written in Rust. It is meant to be somewhat compatible with Linux, but not 100%. The goal is to reduce the bloat, so reduce the functionalities that are legacy or that are not that useful for most applications. This is still an early project, so currently it supports only bash, a few commands, and neofetch, but that's just a start. So for a long time, the performance was not my priority, actually. I just wanted to get something working. So I had a few performance issues. For example, booting was taking 15 seconds on my computer, which is really slow. And the command ls to list all the files on the file system was taking 1 minute and 10 seconds for only 2,000 files. So that's actually pretty bad as on a performance point of view. So I needed to optimize all of that. So the problem is a kernel is a pretty big piece of software. So where do we start? So I needed to have some kind of tool to indicate me where the performance was bad. So I had to basically have a profiler. The thing is, QEMU does not have, to my knowledge, a tool that allows to do that. So I had to do it myself. To do so, I first tried to make what's called a performance profiler. So that's basically using the JDB debugger to interrupt the execution of the program periodically and just get the stack, the call stack each time. And then you just aggregate everything together and you get an overview of the program. The thing is, it's actually slow in practice, too slow for QEMU. So we need another solution. So what I decided to settle for was to write a plugin for QEMU. So the plugin is actually doing pretty much the same thing. So it interrupts the execution, but much faster than JDB can do. And when I have aggregated all the stacks, I basically use a tiny program to make a flame graph with it. So a flame graph looks like that. Each block represents a function, and the blocks above represent the functions that are being called by the function below. The larger a block is, the more time is spent into it. So when I had this flame graph, I could decide which part needed optimization and priority. So I decided to start with the function strlen, which is a function in the C language that allows to get the length of a string. This implementation is actually not very optimized since it's checking 1 byte at a time. The reason why I needed to be implemented in C is because the libcore in the Rust language requires a few functions to be already present and not implemented in Rust because they might be called implicitly by the compiler. So this is why it's implemented in C. So to optimize it, I decided to use this solution, which is using code that actually comes from the Muscle C library. James Fisher has a great article talking about it, but to explain it very quickly, it's basically taking 8 bytes at a time and using 2-bit mask to check that if there is at least 1 byte that is equal to 0. Next, I decided to optimize the hash map collection. So for the context, when I am developing the kernel, I cannot actually use the data structures that are provided with the standard library. This is due to the fact that the standard library is actually panicking when memory allocations are failing. But in the kernel, I need to actually be able to detect when there is such a failure and handle it. So I had to re-implement all the containers myself. My implementation of the hash map was actually pretty bad, so I had to basically scrap it all and redo it. I decided to use the Swiss tables. Matt Kolokondis has a great talk about it at the CPBCon 2017, so I highly recommend you to check it out if you're interested. And also I was using the XOR hash function to basically hash the key and find the place where the value should be stored. That function actually has a problem. It's pretty fast to compute, but it has the issue that the distribution across the hash map is pretty poor. So instead, I decided to use fxhash, which has a much better distribution and it's pretty easy to implement. Next, I decided to optimize path management. So this structure is representing a path to a file. It has a few problems. The first is that when you are building this structure, you need to directly split the path into components. Splitting might not be required for everything you might be doing with the path, so it represents useless memory allocations. But also, each component requires its own allocation, which is pretty inefficient regarding the usage of memory. So instead, I decided to make something that is closer to the Rust standard library. So I have two versions of the path structure. The first is owning the data. So basically, when you are going to build the path, you are going to make a copy. Sometimes you have to do that. But there's also the second version, which is actually borrowing memory from somewhere else. So you are reusing memory that is already allocated. So in this case, it allows you to avoid useless memory allocations. And you can also see that we are just storing the path as a single block. There is no splitting, so it's less memory allocations. But if we need to split the path, we can just use this enumeration, which can be returned from an iterator, for example. And as you can see, it's also borrowing the memory from the path. So you are also not making a memory allocation unless you need it. Next, I decided to clean up the management of files. That's actually a big piece, so I cannot cover all of it, but I will try to do an overview. So the file structure represents a file that is currently open on the system. This structure has a few issues. The first is that it is storing the name of the file, which is actually incorrect, because one file in Unix system can have several names due to the fact that you have hard links on the file system. So you basically have several hard links pointing to the same node. And also it stores the path to the parent of the file. So you have to redo the whole path resolution each time you are accessing the file, which is an expensive operation. So instead, you may want to replace that with other information, such as the ID of the mount point to the file system on which the file is located, and the inode of the file, which is basically the ID that allows to locate the file on the disk. The issue with that is that some file systems don't actually have proper inodes. Instead, the files are being allocated on the fly. So, for example, the KernelFS, which is used by ProcFS or SysFS, for example, are allocating the file when you are accessing them. So we need to find another solution, and the other solution was to basically look at what Linux was doing. So Linux has two fields. The first is basically a structure storing function pointers that allow to make operations on the file. So if you want to read from the file, you have a function. If you want to write to the file, you have a function, etc. And you have private data that is associated to it and can be used by those functions. So to handle it, I decided to write it like that in Rust. That's actually equivalent, even though there is only one field. The nodops trait is basically the prototype for all those functions that allow to perform the operation on the file. And the underlying structure is going to store the private data. So if I can show you an example, the meminfo file is going to return information about the usage of memory on the system. It does not require any private data, so there is absolutely no field inside of the structure. And since its size is 0, then the box that we have seen earlier will not make an actual memory allocation. So this is basically free. Now let's talk about the system calls. Basically, under Unix or a lot of kernels, when a program has to communicate with the kernel, it has to make what's called a system call. So it's basically just a function, a special kind of function call. And those functions can actually take pointers, which can point to strings or, for example, structures. And when the kernel are using those pointers, it has to check that it's actually possible to read or write those pointers. There's an easy solution for that. You can basically just take the pointer and check the data structures of the kernel to see if the pointer is associated to a region of memory that is allocated to the program. But there's a security issue with that. It's when you have done the check, then you are going to use the pointer. But several threads can actually share the same memory space, and it's not impossible for another thread to just decide to modify a region of memory under the time basically between when you are doing the check and when you are using the pointer. So instead, we want to do everything at once. So the solution for that is to copy from or to the user space at the given pointer, and we are going to catch errors. Errors are being caught by basically listening for what's called an interrupt. So it's just the hardware that is saying to the kernel, stop your execution, and basically handle this, and then you can go back to it. And if an error is happening, then we are going to stop the copy and return an error from the system call. Copying actually has a cost, but it's not that expensive. So for the added security, it's more than acceptable. So after all these optimizations, I think that you are willing to see the results, of course. So I ended up with booting in 0.3 seconds, which is 50 times faster than before, so it's great. And the command to list all the files on the file system is now taking 8 seconds, which is 8.75 times faster. So this actually is not that great, but it's due to some optimizations that have not been implemented yet. So I will have to work on it. And I can actually talk a bit about it. So currently, every access to a file on the system is making an access to the disk. So we need to find a solution for that, and the usual solution is to use caching, of course. And for kernels, there are actually a type of cache that we can use, which is called a page cache, which is making use of all the memory that is not being allocated by processes to store some content of the disk that is being accessed often. So basically, we are making use of all of the memory that would otherwise be useless. And it would also be interesting to look at cooperative scheduling. So basically, the kernel currently has only preemptive scheduling, which means that each time the process scheduler wants to interrupt the execution of a process to resume the execution of another process, it has to save all of the state of the process, which is actually pretty expensive. So instead, in some cases, it could be possible to use cooperative scheduling instead, which would be a lot faster since with cooperating scheduling, you can save only the state that you are that you know that you need to save and not everything, so it can reduce this cost. And Rust has a great feature actually for asynchronous code with the async and await keywords. So it's probably worth to check it out, and it could allow to implement that in a very elegant way. So thank you for listening. I have a blog, so I recommend that you check it out if you're interested to know more about the project. And I have a GitHub on which the code is available, so check it out, of course. And remember that a star on GitHub is always appreciated. Thank you very much.